In this video, we're going to talk about p-series. Now, p-series is another one of our favorite series because it behaves very nicely and it's easy to determine convergence or divergence. So here we see the form for a p-series. It's the sum n equals 1 to infinity of 1 over n to the p. Notice the counting mechanism, n is now in the base and p is a constant. It doesn't change as you vary n. So we get 1 over 1 to the p, plus 1 over 2 to the p, plus 1 over 3 to p, and so on. Keeping in mind p is constant. Now if I let p equal 1, that gives us another favorite called a harmonic series. So we end up with the series of sum equals 1, sum of n equals 1 to infinity of 1 over n, which turns out to be 1, plus 1/2, plus 1/3, and so on. This is called a harmonic series, and we'll see how it behaves in a little bit. So let's take a look at some examples on how you're going to identify a p-series. So let's take a look at this example. So here we have the sum, n goes from 1 to infinity, of 1 over the cube root of n. And if you expand it as is, you see it looks like that. So we always want to get it in the form of the sum of 1 over n to some constant exponent. Well, we know that the cube root is the same thing as n to the 1/3. So we end up with the sum as n goes from 1 to infinity of 1 over n to the 1/3. This is a p-series with p equaling 1/3. Okay, next we see a series that we've been working with a lot, and that is the sum n goes from 1 to infinity of 1 over 2 to the n. We've seen this one over and over and over again in previous sections. So we have 1/2 plus 1/4 plus 1/8 plus 1/16. So we know this series, but look at what's changing. Where is the constant? The constant is not in the exponent, it's in the base. So n is the exponent, and that's what's changing. So this is not a p-series. This is a geometric series where the common ratio is 1/2, because I multiply 1/2 times 1/2 is 1/4 times 1/2 is 1/8, and so on. So be able to identify a p-series versus other series. So now let's talk about the convergence or divergence of a p-series. This is why we like a p-series so well. Once you identify a series as a p-series, you can easily determine its convergence or divergence. So here's my typical p-series, and here's the rule. It diverges if p is between 0 and 1, where 1 is included. It converges if p is greater than 1. Okay, so let's take a look at some examples and sort of go into more detail as to why the p-series works that way. Okay, so here's the examples. We want to ask, does the series converge or diverge? So let's look at this. Here we have the sum n equals 1 to infinity of 1 over n to the 0.8, or 8/10. Well, this is a p-series because the counting mechanism is in the base of the denominator, and my p is constant, and it turns out to be my p is 8/10 or 0.8, which is less than 1. That falls into the diverge category. That is all you need to do to determine whether a p-series diverges or converges. Let's look at another example. So here we have our p-series that we talked about earlier, our harmonic series. So we have the sum from 1 to infinity of 1 over n well, we saw that before. That's 1 plus 1/2 plus 1/3 plus 1/4 and so on. Well, P equals 1, and that's at the very end of that interval that determines divergence. And it is my harmonic series, so it diverges. Now, what do I got next? Okay, so let's talk about this for a second. Well, let me go into that later. Here's another example. If I have the sum n equals 1 to infinity of 1 over n to the 1.04, okay, it's in the format for a p-series. A constant at the exponent, the base is the counting mechanism, so p equals 1.04. That's just barely bigger than 1, but that's all it takes, and that one converges. Okay, so now let's talk in more detail about why does a harmonic series diverge and one that is 1.04 converges? Well, if we look at an example here, we have 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25. Now we're supposed to determine if this diverges or converges. So what we do is we take a look at it. Let's rewrite it to see if we can recognize it as a p-series. So I know 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, 25 is 5 squared, and so on. So we see that the base is changing, but it's always being squared. So that means I can convert it to this summation notation, and n equals 1 to infinity, my sum of 1 over n squared. So that's a p-series with p equaling 2. So 2 is greater than 1, so it converges. So now think about this. Let's compare this series to the harmonic series. It seems like the terms are getting smaller, aren't they? Yeah, they are. And so are the terms in the harmonic series. But the terms in this example are getting smaller at a faster rate versus the harmonic series. So these pieces aren't getting small enough so that every time you add them on, they make a difference. These pieces, each term that you add on at the end is growing small so much faster that they don't make a difference. So that's why this series does not converge and this series does. Okay? So let's go on and let's take a look at some more examples. Let's look at this problem. And this is number 42 for my class. This is number 42, page 623. And it says, does this series converge or diverge? Well, you look at this problem and you say, okay, the counting mechanism is in the base. The exponent is pi. Don't be fooled by pi. Yeah, it's a symbol, but pi is a constant. And we know that pi equals approximately 3.14. And that is greater than 1. So there you have it. It converges. That is all you need to determine whether it converges or diverges. Let's take a look at another example. For this problem, it's number 46 in our text. I see that n equals 1 to infinity. I'm doing the sum of 2 over the 5th root of n squared. Now we want it to be in this format. Oops. Let me slide that over a little bit. The sum n equals 1 to infinity of 1 over n to the p. Well, let's see. I need to get rid of that 2, don't I? So let's make this guy equal to 2 times the sum n equals 1 to infinity of 1 over the 5th root of n squared. So now we can convert that to a, oh, and let me move that 2 out of there. So I can convert that to a rational exponent. And now I have my format, sum n equals 1 to infinity of 1 over n to the 2/5. This is p. And my counting mechanism is in the base. So p equals 2/5. 2/5 is less than or equal to 1. So my p series diverges. And that is it for convergence and divergence of a p series and identifying a p series.